Okay, so here's the first FRQ for Unit 6, progress check. Here we have a bar and a sphere. They're connected by this pivot point, and there's a little spring in between them, and the spring's going to basically launch the bar and the sphere away from each other, and they're going to rotate with respect to that pivot point, and then there's a locking mechanism that locks them together after the spring is launched. So something that's a little confusing about this diagram, this is a top-down view, so gravity is not going to play any role, right? So imagine that this pivot point is on a table, okay, and the bar and the sphere are rotating parallel to that table. Okay, so we're going to ignore gravity in this problem. So it seems a little confusing until you actually read through it. So one thing is important to note: the bar has a moment of inertia of 1/3 ml squared, and the sphere is going to have a moment of inertia of ml squared because it's a point mass, and they both have the same mass. And then for part A, we got to indicate whether or not it rotates clockwise, counterclockwise, or not at all after the mechanism has locked. And basically for this one, it will not rotate. Okay, it will not rotate after locking. And the reason it will not rotate after locking is because moment of inertia has to be conserved, right? So I misspoke. Angular momentum has to be conserved. Angular momentum has to be conserved. So the bar and the sphere, they start with 0 angular momentum. And this spring is actually considered to be internal to the system, right? So if I look at this system here, all right, I see the bar and the sphere. They initially start not rotating. And then as soon as the spring is launched, what's critical is the spring is launched in such a way that it doesn't have any angular momentum itself, right? It just falls straight down. This is a top-down view, so it looks a little confusing. But what's important is that if it starts with no angular momentum, that spring is an internal force, right? And it's going to generate an internal torque. The angular momentum of the ball is going to be equal and opposite of the angular momentum of the bar. And as soon as they lock together, they're going to stop rotating, right? So that's basically the answer for this problem, is because this is the initial angular momentum was 0. Therefore, the final angular momentum is 0. And that's just I naught omega naught equals I naught, or IF omega F. And because omega naught is 0, then omega F has to be 0. Okay, they have equal and opposite angular momentum while they're rotating, and as soon as they lock together, they will no longer rotate. So assume the bar and rod are approximately parallel at t equals 0, and the spring takes a very short amount of time to push them apart. Now we have to derive the value of the angle theta b, that's the theta of the bar, which the bar rotates from a starting position, and we are going to basically use the same equation, conservation of angular momentum. So I know the initial angular momentum of the system is 0, and that has to equal the final angular momentum, which is also 0. But what we're going to do to derive the angle that the bar rotates around from its initial position, right? So basically, this is the initial axis here, and the bar is going to rotate with respect to that axis, right? So the bar is going to rotate and the sphere is going to rotate. I know in this diagram, it's not obvious what the relationship between the rotation is, but we're going to have to calculate that. So in other words, they are going to have, while the bar and the sphere are rotating, they're going to have equal and opposite angular momenta. So let's write down an expression. So I'm going to say that the angular momentum of the bar times the omega of the bar while it's rotating, so before the mechanism locks, has to equal the moment of inertia of the sphere times the angular velocity of the sphere. And now let's write down the equation. So I have 1/3 ml squared. What did they use? L? Yeah, they use L. So 1/3 ml squared times omega of the bar has to equal the moment of inertia of the sphere, which is ml squared, times the angular velocity of the sphere. And as we can see, the ml squareds, they cancel out. right? So in other words, the angular velocity of the bar is going to be 3 times the angular velocity of the sphere, right? So it has 3 times the angular velocity of the sphere. And what's important for this problem is we know that when they lock together, they're 180 degrees apart. Okay, so we have it in terms of omega. We need it in terms of theta. Well, I know that theta or omega is equal to theta over t, right? And the t is going to be the same for both of the objects, right? So I have theta of the bar times t. Whoops, I'm going too fast here. All right, so 3 omega s. Yeah, so the angular velocity of the bar while they're rotating is 3 times the angular velocity of the sphere, because the sphere has 3 times the moment of inertia. And so now let's write it out in terms of theta. So I have 3 times theta s times t, and then obviously those t's cancel out as well. And now we just have this relationship. So the theta of the bar is equal to 3 times the theta of the sphere. And something else that's important to note is that that's not enough. Just writing that down, you have to actually figure out what the angle is, okay? Because we know that the angle between them after they lock, they're 180 degrees apart. So in order for the bar to rotate 3 times as much as the sphere, I can draw a little diagram here. So let's say that the bar and the sphere, they start off 0 degrees apart. Now, I can't make it exactly 0, right? In the case of my picture, right? I'm trying to distinguish between the bar. So this side's the bar, this side's the sphere, all right? So if we think about it, they have to be 180 degrees apart. And for the sphere to rotate, or for the bar to rotate 3 times as much as the sphere, I know that theta of the bar plus the theta of the sphere has to equal 180 degrees, right? So that means that the bar, since the bar has 3 times the angular displacement as the sphere, okay, I can just rewrite the expression. So I can say, I can solve it in terms of theta b. So I'm going to write theta s as 1/3 theta b, right? Actually, for me personally, I think it's easier just to write in terms of theta s. So I have 3 theta s plus theta s equals 180. So then that means theta s equals 3 plus 1 is 4, and then 180 divided by 4, that's 45 degrees, which means the theta for the bar is 135 degrees. All right, and that's your answer. So 135 degrees. And if you think about it, I'm going to draw the after picture. So the sphere is going to rotate about 45 degrees. So here's going to be the sphere. All right, that's the 45 degrees for the sphere. And then the bar is going to rotate from its initial, come on. All right, there we go. That's my bar. All right, and that bar rotated 3 times as much, which is 135 degrees, totaling to 180 degrees. So that's part 2 of part A. All right, so now we have this equation here. It says here that the spring causes initial separation, and after the fact, the sphere has an angular speed omega s, and we have to figure out the force results in a torque about the pivot of magnitude tau. And the magnitude tau of the torque exerted on the sphere by the spring as a function of time can be modeled by the following equation. Okay, so the torque is equal to the initial torque times the cosine of pi times t over 2 times t1. And then t1 is basically when the spring, let's see, for a short time interval. Okay, so like basically once the spring gets released. All right, so this T0 to T1 is the spring is pushing against the bar, the end of the bar and the sphere at the same time. actually, this equation is this is specifically the torque exerted on the sphere by the spring. Well, it should be equal and opposite torques anyway, so you can think of it the other way around too. But this is specifically the torque on the sphere by the spring. We had to derive an expression for T1 in terms of L, M, tau naught, and omega s, and physical constants as appropriate. So in order to do this, what we need is the impulse momentum theorem for angular momentum, right? So we have here tau, right? So torque times time is equal to the change in angular momentum. We know that the angular momentum of the sphere is going to change, right, and become the moment of inertia of the sphere, right? So it starts off at 0 and it's eventually going to reach some value. That's the moment of inertia of the sphere times omega s. But here we have to actually integrate. Okay, so we have to use the integral definition. Okay, so if I want to calculate my change in angular momentum, I have to integrate my function, right? So the thing is, my torque is not a constant value. My torque is changing with respect to time. And because it's changing with respect to time, we have to integrate that function from t equals 0 all the way to t equals t1. All right, so now let's integrate our function. Let's see here. We have, so the torque acting on it is T naught, or tau naught, times the cosine of pi times t all over 2 times t1. All right, so t1's a constant, right? So t1 is the amount of time that the spring is actually pushing on the sphere. The variable t in the numerator is the actual variable that we're integrating. So so I know it's a little confusing. So t1 is a constant value, and the t in the numerator, that's the variable that we're integrating. So we're integrating this with respect to time. Okay, and then we know that the integral of cosine is going to equal negative sine. All right. So when we actually perform, or actually, hold on 1 second. Whoops, I almost made a huge mistake. Okay. The derivative of sine is cosine, and the derivative of cosine is negative sine, and the integral of cosine is sine, because the derivative of sine is cosine. Oh, got to be careful. Yeah, so the integral of cosine is equal to sine. Okay, so cosine of x is equal to sine of x. All right, anyways, so yeah, so we're going to now perform the integral. And because I have all these values within the cosine function, right? So say I have like, so say I took the derivative of sine of c times x. All right, so for this one, what you have to do is it would be, you take that constant that's in front of the variable x, okay, and then you'd get c times the cosine of cx. And then if you do the integral, all right, so say I do the integral of the cosine of some constant times x, okay, that's going to give me 1 over c times the sine of cx, okay? So that's like the functional form we're going to use. So this constant here in front of t, right, that's the pi over 2 t1. All right, so when I integrate this, right, for my indefinite integral, I have the initial torque, T naught, times 1 over c, right? So for here, pi divided by 2 t1, that is the constant in front of the variable. Okay, so then 1 over that is 2 times t1 over pi. Right, these are my constants, and now I'm going to have to evaluate the integral. So the integral of cosine is sine of pi times t over 2 t1. All right, and then I'm going to evaluate that integral from t equals 0 to t equals t1. All right, so then I'm going to plug everything in. All right. I know that the change in angular momentum of the sphere, right? So delta L, right? So it starts off with 0, and then after the spring pushes on the sphere, it's going to have some angular momentum ml squared times omega s, okay? I know I'm writing really small, but it's just I don't have much space here. So here I have, so m L squared times omega s is equal to the initial torque times 2T1 over pi. And then I'm going to do the full evaluation just so you can see what this looks like. So I'm going to start, you start with the upper bound, and then you subtract the lower bound from that, right? So then I end up with, so when t equals t1, right, I'm going to have the sine of pi times t1 all over 2 t1. All right, well, those t1s cancel out, so I'm just going to cancel those out right now, okay? And then that minus the sine of pi times 0, right? So that's the lower bound, divided by 2t1. All right, and now let's actually evaluate what these values are. Well, the sine of pi over 2, that's equal to 1. And then the sine of pi times 0, all right, well, anything times 0 is 0. So the sine of 0 is actually 0. So it's basically just 1 minus 0. All right, so that's when I evaluate my integral from t equals 0 to t equals t1, I end up getting, well, just 1. All right, so then my final answer, all right, now we have to solve for, t1. So I have ml squared times omega s is equal to tau naught times 2t1 over pi times 1, right? Because that's what our integral ended up coming out to. So solve for t1, I'll multiply both sides by pi, and then divide it by 2 times tau naught. So then t1 is going to equal ml squared omega s times pi all over 2 tau naught. Yeah, so that's pretty much it. All right. Okay, so a bit of an interruption, but we're moving on to the second FRQ. So here we have a hollow cylinder. It's sliding without rotating in a region with negligible friction, and then it enters a region where there is some friction. There's some kinetic friction where it's rotating and slipping at the same time. And then eventually the cylinder slows down enough to where it begins to roll without slipping, right? So for this one, what we need to do is we need to start by drawing a free body diagram. And what the free body diagram for this cylinder, what it looks like. So I would always recommend starting with the force of gravity, right? And what's important about the free body diagrams for objects where the rotation matters, where there's a torque, is that the location of the force is very important, right? So the force of gravity, right, that the Earth exerts on the cylinder, that's going to originate from the center of mass, okay? And then the normal force, well, it's contacting the very bottom of the cylinder and pushing up on it with an equal magnitude to the force of gravity. And then the friction force, in this case, is actually pointing to the left. And the reason why, if we look at our situation here, well, let's think about it. So the bottom of the cylinder, right, the cylinder is not rotating at the beginning. So then when it enters this region where there's friction, the bottom of the cylinder is sliding to the right, okay? And the friction force between two surfaces, well, it opposes the motion between those surfaces. So if the cylinder is sliding to the right while the ground is stationary, well, the ground is going to exert a friction force on the cylinder that's going to be going opposite of the motion, right? So the cylinder is sliding to the right, and the friction force is going to be going to the left. All right, so that's the important distinction for that free body diagram. Then for part B, we have to derive an expression for the amount of time it takes for the cylinder to rotate without slipping. All right. So at the very beginning, it's rotating while slipping, or actually in the very, very beginning, it's not rotating. But then t naught at t equals 0, it starts to rotate while slipping as the kinetic friction is acting on the cylinder. And then at time t equals ts, that's when it's no longer slipping. All right. And here, the way we're going to approach this is we're going to use, we're going to set up our net torque and our net force equations. So for the net force, we know that equals ma, and that equals the sum of the forces. So the force of gravity and the normal force, they're equal to each other in opposite directions. So they're going to cancel out. And then the only force that's remaining is going to be the force of friction. And we know that the force of friction is going to equal mu times the normal force, right? That's kinetic friction in this case. So in the middle region, it's kinetic friction. So here, I know that the normal force has to equal the weight of the cylinder. So then the force of friction, I can rewrite that as mu times mg. So the net force is equal to mu mg. The m's are going to cancel out, and I know that the acceleration that the cylinder experiences is going to equal mu times g. All right, but we need to solve for the time it takes to start rotating without slipping, right? So in the middle region, it is slipping and rotating, and it takes some time until it rolls without slipping. So what I'm going to do is I'm going to write an expression for the acceleration in terms of time that relates it to v naught. And the expression we'll use is the first kinematic equation. So I know that if I have some initial velocity and I'm accelerating, okay, my final velocity is going to equal my initial velocity plus a times t. All right. And I know that a is equal to mu times g. So I'm going to rewrite this as Vf is equal to V naught. So this part is important. So understanding that the acceleration, I wrote everything in terms of the magnitudes, right? But this object is moving to the right. All right, so its initial velocity is moving to the right, but it's going to be decelerating, right? Because the friction force is pushing it to the left. All right, so I'm just going to, I'm treating mu and I'm treating g as positive constants. All right, so I know since it's going to be decelerating, I'm going to put minus mu times g times t. And that's my equation for the velocity of the cylinder. So now we need to relate it to the angular acceleration. All right, so we have to look at the net torque. So I looked at my net force. Now let's look at my net torque. I know that's equal to I times alpha, okay? And the torque caused by friction is going to equal the force of friction times the moment arm, right? So torque is equal to R times F, right? Or R cross F, RF sine theta. But it's acting at a right angle with respect to the moment arm, right? So with respect to the radius of the cylinder, the force of friction is acting at a right angle. So it's just R times F, okay? And here, I know the force of friction equals mu mg, right? So I can write this as mu mg times r. Now to relate this to the angular acceleration, right? So I have I times alpha, and I know since this is a hollow cylinder, that's going to be mr squared, right? So mr squared is the moment of inertia of a hollow cylinder times alpha, all right? So then what I can do is I can write alpha in terms of these variables. So I'm going to do alpha is equal to mu mg times r. That's the torque acting on the cylinder. And then if I divide that by the moment of inertia of the cylinder, right, I have mr squared times, actually, that's just it. That's the moment of inertia. So mr squared times alpha, that's the net torque on the cylinder. And then that has to equal the torque caused by friction, because that's the only torque that's actually acting on the cylinder. So let's cancel out some of the terms. The m's are going to cancel out. One of the r's are going to cancel out. So I just get mu, mu naught, because that's what they use here. They say mu naught. So mu naught times g divided by r. All right, that's my angular acceleration. And then to relate it to the linear acceleration, what's important to note is our relationships between angular motion and linear motion. Okay, so we have these relationships. Okay, but something that's important, this is only true, all right, so like the v equals r alpha, okay, or I'm sorry, v equals r times omega. This becomes true when it's no longer slipping. Okay, so it's when it's rolling without slipping. Okay, so basically what's happening here, if you want to visualize the problem, the cylinder starts with no angular velocity, and then it starts to pick up some angular velocity as the force of friction exerts a torque on the cylinder, and then it reaches a point where the tangential velocity of the cylinder, right, if I look at the surface of the cylinder, the tangential velocity is going to be equal to r times omega. Okay, so here, this is true only when it's rolling without slipping. So the v equals r omega. So I'm going to use that in order to solve for this problem. So I have an expression for alpha, I have an expression for the acceleration, and now I need to combine these two ideas. So my expression for v, all right, once it reaches, right, the v is going to be when it reaches that point where it's rolling without slipping. All right, and then omega, well, I'm going to use the same kinematic equation, except the rotational version, right? So omega f is equal to omega naught plus alpha t, all right? This time, I could just define the a clockwise rotation as positive, right? So this angular acceleration, I'm going to consider it to be a positive value. At the very start, at t equals 0, well, omega naught is 0, right? So it's not rotating before t equals 0. And right at t equals 0, that is when it begins to pick up some rotational velocity, right? So omega naught is going to be equal to 0. And I have this expression for omega. All right, I'm going to just use omega instead of omega f. So omega equals alpha times t, which is mu naught g over r times t. And then using this expression, the condition for rolling without slipping, that's when the angular velocity is going to be equal to the linear velocity, right? So I have here omega is equal to mu naught g times, mu naught g over r times t. So then I'm going to rewrite omega in terms of v. So omega equals v over r. And then I have here, I'm just going to write it out step by step. So we have omega equals mu naught g over r times t. So then rewriting this in terms of v, I have v over r is equal to mu naught g over r times t. Okay. And then the r's cancel. I have v is equal to mu naught g times t. But I also have another expression for v, right? So my expression for v as a function of time, right? Because ultimately what we're trying to do is we're trying to find the time in which the time it takes for it to roll without slipping. So my expression for v, right? So what's the velocity once it reaches ts, right? So it's going to be slowing down, right? So v naught is not equal to the velocity at ts. All right, so I'm going to rewrite this as v naught minus mu g times t. So this expression I came up with over here. All right, so I have v naught minus mu times g times t. That has to equal mu. All right, so using mu naught, because that's mu naught over here. So mu naught times g times t, and then I move that over to the other side. So the initial velocity is actually 2 times mu naught times g times t. Okay, so the final velocity, all right, this is ts. So the final velocity is actually going to be half of what the initial velocity is. So this thing is sliding without rotating, and then the friction force is going to be slowing it down. It's going to be slowing down the linear velocity of the cylinder, and then the cylinder is going to gain angular velocity until it reaches a point where it's rolling without slipping, and then the angular velocity is directly related to the linear velocity, where v is equal to r times omega, right? So in terms of, you can also kind of think of it in terms of, I want to say in terms of energy, but just think if it's gaining angular velocity, right? So it didn't have any angular velocity before, and it's gaining angular velocity, all right, it's going to be losing linear velocity up to a point to where the linear velocity is directly related to the angular velocity. But anyways, we need an expression for Ts. Oh, my thing just passed out. So this is my expression for V naught, and then to solve for Ts, I just got to divide both sides by 2 times mu naught G. So Ts is equal to V naught divided by 2 times mu naught times G. Then on the axis below, we have to sketch the graphs. So I know that I start off with some V naught, right? So I'm going to start off with some V naught over here. I don't have to label the axes, but I'm going to do it anyway, just so we understand what's going on. So I start with some V naught, which is equal to 2 times, what did I get? 2 mu naught G times Ts. And then it's going to reach some final velocity that is equal to mu naught G times Ts. All right. So I start here. All right. As the sphere begins to rotate while slipping, it's losing linear velocity until it reaches its velocity when it's rolling without slipping. And then for the angular velocity, well, it starts off at 0, and then it gains angular speed until it rolls without slipping. All right. So anyways, that's the situation. And to label this axis, right, that's going to be the expression for omega, right? So I have the expression for omega over here is mu naught G over R times T. That's going to be what the value is. So here we have the cylinders taken to another similar surface where the coefficient of kinetic friction between the rough section and the cylinder is mu1, and mu1 is greater than mu naught. The cylinder slides and rotates for time t2. And how does t2 compare to ts? Well, if mu is larger, right, then the force of friction has to be larger. If the force of friction is going to be larger, okay, then the amount of time it takes to accelerate, right, to give this cylinder an angular acceleration to reach its final rotational velocity, it should take less time, right? So basically I have more torque acting on the cylinder, right? If I have more friction, there's more torque acting on the cylinder, and it's going to take less time to get it up to speed in terms of rotation. And in terms of justifying it for my expression for Ts, well, notice mu naught's in a denominator, right? So Ts is equal to, what do we have? We have V naught over, right over here, we have V naught over 2 times mu naught times G, all right? And since mu naught is in a denominator, so mu is in the denominator. In other words, it's inversely proportional. To the amount of time it takes to reach the non-slip condition where it's rolling without slipping. So if mu1 is greater than mu naught, right, then that means that T2 has to be less than TS. All right, and that's how you approach that one. For the next problem, I think it's the lab one. Yeah. So it's a lab-based question. We have a platform with an irregular shape, and it can rotate freely with negligible friction. And we want to determine the rotational inertia of the platform. So they have a collection of small metal balls the same size, but they have different known masses, and a launcher that can launch the metal balls at a fixed known velocity, VL. And they want to launch the balls horizontally to the same location where they get stuck, and the platform is going to start to rotate, right? So these balls are going to hit the platform, and because the balls have angular momentum with respect to the axis of rotation, then that means that this contraption, this platform, is going to begin to rotate. So we have to design an experimental procedure to determine IP, right? So the moment of inertia of the platform, and we need to provide enough details so the experiment can be replicated. So basically with this one, this is where you have to write out the procedure, right? So here I have the, I'm just going to say it. I'm not going to write it down, right, for the sake of time. So basically you want to launch the metal balls of known mass. You want to measure the angular velocity of the platform after the fact. So once the ball hits the platform is going to start to rotate. Actually, one thing that's mentioned in the scoring guidelines that I like, they say to measure 10 revolutions. So it's going to be rotating, and you want to measure, whoops, I don't have the edit feature on, markup. There we go. So one thing that I liked, which is a good experimental procedure. So you're going to want to measure 10 rotations. And this whole idea of measuring, like, why measure 10 of something? Well, the whole point is you're reducing your experimental uncertainty, right? So if you measure any sort of periodic motion, right, like a rotation or like a pendulum or anything like that, or a spring, if you measure 10 periods of that object, okay, you can find the average, right, simply by dividing by 10, right? So whether or not it's the period of a pendulum or the rotation rate of this platform, by measuring 10 revolutions, okay, it's very easy to just divide by 10 to get what the angular velocity is. And that also reduces your uncertainty. So your timing, right, whenever you do perform a time measurement, there's some uncertainty in your time measurement based on your reaction time. So by measuring 10 of that, you basically just move the decimal point. You're reducing your uncertainty by a factor of 10 as well. So it's just a nice, neat little trick to measure, the period of the amount of time it takes to reach 10 rotations, right? And dividing by 10, that is going to reduce your uncertainty. So something else to mention, you want to talk about the equipment you're going to use. So we would measure 10 rotations with a stopwatch, and then you'd have to do multiple measurements, right? So you're going to repeat the measurements for different metal balls with different known masses. You're going to want to record each measurement. So your timing measurement, right? When you time the amount of time it takes to achieve 10 revolutions, you're going to want to do that multiple times and then find the average value. Okay. And then finally, what else you need to know to find the rotational inertia, you have to measure this distance d. So how far away is the ball from the axis of rotation? Because the thing is, the velocity is known, right? So it tells you in the experiment that they already know what the velocity is, right? So the other thing that we have to measure is how far away the ball is from the axis of rotation, because that's going to tell us the angular momentum of the ball, right? So like the angular momentum of the ball is equal to the mass of the ball times the velocity of the ball, which, what do they label the velocity as? VL. So like the launch velocity. So times the launch velocity of the ball times d, that's going to be the angular momentum of the ball. All right, and that angular momentum of the ball is going to equal the angular momentum of the system after the collision because of the conservation of angular momentum. And then from that, you can figure out the moment of inertia of the platform, which is what we'll be doing for part B. So how would the students create a linear graph, and how would that graph be analyzed to determine the moment of inertia of the platform? Well, here I'll write out the whole thing. You don't need to do this whole process, but I think it's helpful in terms of experimental design. So let's just kind of go through what the equations are going to be. So I know that, the initial angular momentum is equal to final angular momentum, and I have the mass of the ball times launch velocity times d. That has to equal the final angular momentum. So that's going to be the moment inertia of the platform. But it's also the moment of inertia. I'm sorry, the moment of inertia of the sphere. So the sphere is going to be embedded into the platform after the collision. So that sphere still has angular momentum. That sphere is going to have less angular momentum than it did before, right? Because the total angular momentum is conserved, but the sphere itself still has angular momentum. So I have to add, right? So it's going to have some angular momentum, mass of the ball times the distance from the axis of rotation squared, all of that times omega, right? So the omega is what we measure, the angular velocity. Okay. Now, in terms of setting up the experiment, like what do I graph? For this equation, it's actually a little annoying. So my independent variable, right? So let's think about how we set up this experiment. So the thing that you're changing as the experimentalist is going to be the mass. So I have the mass is my independent. And the thing that depends on that, right? So what are we measuring? We're measuring the rotation rate. So we're measuring omega. That's the dependent variable. Omega depends on the mass. Now here's where it's annoying, because I have a mass term on the left-hand side of the equation, but I have a mass term on the right-hand side of the equation, and that's also multiplied by omega. So we're going to do some algebra finagling in order to get this equation in the right format. And the easiest way to do that is I'm going to solve in terms of omega, right? So I just divide both sides, right? Because that's my dependent variable. Okay, so my omega depends on the initial angular momentum of the ball, and I'm going to divide that by the moment of inertia of the system after the collision. So the moment of inertia of the platform times the moment of inertia of the ball, or plus the moment of inertia of the ball. Okay, so I'm going to make that a little bit more obvious. So moment of inertia of the platform plus the moment of inertia of the ball. And then basically I need to get the mass term for the ball by itself. Okay, so one thing I can do. Would I? Oh yeah. Okay, this is fine. All right. So one thing you can do is I can take the inverse of this function, because if I look at this fraction and I look at the inverse of the fraction, well, the MB, right? So I have an MB up here and I have an MB down here in the denominator. All right, but they don't cancel out in this manner. However, they would if I flip it. So if I do 1 over omega, then I have the moment of inertia of the platform plus the moment of inertia of the ball, all divided by the angular momentum of the ball before the collision. Okay, and then I can separate this fraction as moment of inertia of the platform over the angular momentum of the ball plus this. Okay, and if you notice, now one of the m's cancels out. So this m over here on this part of the expression, right, these cancel out. So one of the m's cancels out, and then one of the d's cancel out. All right, and then I have just this final expression. So I have 1 over omega. Whoops, let me go back to my smaller pen. So 1 over omega is equal to the moment of inertia of the platform over the angular momentum of the ball plus d over the launch velocity. And these two terms are constant. All right. So if I want to map this to an equation, right, I can kind of write it like this, right? So my mass is my independent variable. So I have 1 over omega is equal to this divided by the launch velocity times d. So all of that times 1 over m plus d over VL. All right, and those are constants. So then when I want to map this to like a graph, all right, so what do I graph in order to get the mass of the, in order to figure out the moment inertia of the platform? Well, for my vertical axis, I'm going to put 1 over omega. For my horizontal axis, I'm going to put 1 over m. So I'm going to measure inverse angular velocity, and I'm going to write inverse mass on the horizontal axis. And then the slope of that graph is equal to this expression. And then this here, this is going to be the y-intercept. So the y-intercept is this distance d over the launch velocity of the ball. Okay, so then in order to figure out the moment of inertia of the platform, I know that the slope is going to equal this. So then to calculate the moment of inertia of the platform, it's the slope times the launch velocity of the ball and the distance that the ball is from the axis of rotation. So this is a bit much, and it's annoying when the equations don't necessarily cooperate, but this happens. All right, I remember in the previous practice set, there was a experiment where we had to actually use the y-intercept to figure out the value that we're trying to measure, right? We didn't even need to care about the slope. So anyways, that's how you approach this one. This is how you would determine the moment of inertia of the platform. And now here, there's a different experiment. So now we have a dart of known mass, and it's going to attach to the circular platform. And the thing that's a little bit tricky about this has to do with the fact that the dart's going to rotate with the platform, but also notice how the dart is some distance y away from the axis of rotation. However, the dart, in terms of its angular velocity, right? So in terms of its angular momentum after the collision, well, it doesn't depend on y, because the dart can hit any possible value of y. It actually depends on the radius of the dart with respect to the center of the circular platform. So you're going to see that makes it a little bit more tricky, but it's the same equation, right? Conservation of angular momentum. So here we have a data table, and we need to indicate what we're going to graph in order to get a straight line. All right, so basically they make you do it twice, except for a different experiment. They're really making sure you know how to draw these graphs. So let's just write out the equations here. I know conservation of angular momentum. The angular momentum of the dart before the collision. Well, the circular platform is not moving, so it doesn't have an angular momentum, but the dart does, right? Because it's some distance away from the axis of rotation. Okay, so that's going to be the mass. What do they use for the dart? md. So md times the velocity, L, the launch velocity, times y. Okay, that's going to be the moment of inertia, the angular momentum of the dart. And then the final angular momentum, right, it's similar to what we saw in the previous problem. It's a combination of the dart platform system. So we have the circular platform. What symbol do they use for it? So they use IC. Yeah. So it's like circular platform. Okay, so we have circular platform plus the moment of inertia of the dart, except now for this one, okay, it's going to be the mass of the dart times this radius, okay, because that's going to be the distance from the axis of rotation, okay? It's going to be rotating about the center, okay, so we don't use y, we use the r sub d, so it's r d squared, all of that times the final angular velocity of the system. All right, and now my independent variable. So the independent, again, it's what you are changing as the experimentalist, and then the dependent is what you're measuring. So the thing that we're changing is the y. In the previous experiment, we were changing m. But in this experiment, we're changing y. We're changing the vertical distance, the distance from the axis of rotation of the dart. So I need to write y, or I need to write omega in terms of y. So what I'm going to do is I'm just going to divide both sides of the equation here. So omega f is equal to the mass of the dart times the launch velocity times y, all divided by the moment of inertia of the circular platform plus md times r sub d squared. And in terms of setting that up as an equation, right, well, I can just do this. I can separate out the y, which is our dependent variable, our independent, I'm sorry. That's our independent variable. Dependent is the omega plus md r sub d squared. So all of that times y. And then again, it's the same process for linearization, right? So I have here my vertical axis is omega, my horizontal axis, okay, is going to be the distance from the axis of rotation, y, and then finally my slope is this giant expression over here. At least there wasn't too much algebra finagling like with the previous one. So yeah, that's it. So horizontal axis, that's going to be the independent variable. All right, that's going to be y. And then for my vertical axis, that's going to be omega. Now, in terms of actually performing the calculations, I'm not going to do that for the sake of time. You can look at the scoring guideline and try them out for yourself to make sure you're doing it right. And then, does it ask about the... No, so it doesn't ask about the slope, or at least not yet. All right, so then you get the data, draw a straight line, and then use the line drawn in part C, calculate the experimental value for the mass of the dart. All right, so let me just show you what it is on the scoring guideline. So we'd want to use this, our horizontal axis is y. Okay, so if you measured the slope by hand, you should get this value. And then one thing that's very important when you're calculating the slope, so here, notice that I have my data points here. I have 4 data points here, but the points that I use to determine the slope of the line, I have to use points that are on the best fit line, not data points. Okay, so I draw a best fit line, okay, that fits through all the data points, and I pick 2 points on the best fit line in order to determine the slope of the line. All right, you can't determine the slope from the data points. You have to do the slope from points that are on the line, that are not necessarily data points. Yeah, so that's pretty much it. All right, so now for the last one, almost there, we have this situation. Okay, so we have 2 cylinders, and they're rotating about an axle, and there's some mechanism to slide the rod so that one cylinder comes closer to the axis of rotation, then the other cylinder gets further away from the axis of rotation. So we have to indicate whether or not omega 2 is greater, less than, or equal to omega 1. So omega 2 is the new velocity. All right. So justify the claim without deriving or manipulating any equations. All right, so I'm a little low on space here. I'm not going to write out like a paragraph. But basically, the argument is, if we think about it, okay, more of the mass is going to be distributed away from the axis of rotation, okay? Right, so now the center of mass of the system is shifted, right, from the axis of rotation, right? So you can think of it in terms of parallel axis theorem, right? That's going to increase the moment of inertia. Me personally, I think of it as a mass distribution, right? So now I have this cylinder, it's that much further away from the center. And I'm just going to go through the calculations just so you can see it. But basically, if the moment of inertia, right? So the argument is that, oh, whoops, I always forget to do this. Okay, so the argument is that the moment of inertia, so this is I2, that has to be greater than I1. Okay, so as I slide this mechanism over to the left, or I slide it away from the original position, the mass is going to be distributed further from the axis of rotation. And we know that the function is mr squared, right? So in terms of working it out, all right, I know that the angular momentum is going to be conserved. There's no external torque acting on the system. The reason why is that even if this mechanism is pushing on the rod, right, like exerting some force to move it, well, that's going to be parallel to the moment arm, right? So it's actually not going to exert a torque, right? So say it's pushing it out, well, then it's not going to be exerting a torque because it's parallel to the lever arm, okay? Right now, if I was pushing it, like so basically, so this is pushing it out, and then the lever arm is in the same direction, okay? So there's no torque being exerted on the system, right? So you would say, net torque is 0. Okay, so if net torque is 0, the initial angular momentum has to equal the final angular momentum. Okay, so I2 omega 2. And if I2 is bigger than I1, right? So I2 is bigger than I1. Well, then that means that omega 2 has to be less than omega 1 because the conservation of angular momentum. In order to write it out as an expression, let's see, where do I have some space here? Not much space. All right, so anyways, the basic idea is let's calculate I1. So let's calculate this situation. So here, the distance from the axis of rotation for the cylinders is L over 2. And then the problem, we're not going to worry about the rotational inertia of a cylinder because it says here that, where is it? The center cylinder is rotates negligible friction. The radius cylinder, the radius of the cylinder is small compared to the length L. So because the radius of the cylinder is very small, we don't have to use parallel axis theorem, right? We don't have to worry about the moment of inertia of the cylinder. You can basically just treat it like a point mass. So that's basically what we're going to do. We're going to treat these cylinders as point masses in order to calculate the moment of inertia. So if I do that, all right, so I have L over 2 over here, and I have L over 2 over here. So this cylinder has moment of inertia, and this cylinder has rotational inertia. And we know that it's going to be, for a point mass, it's basically mr squared, and then r is equal to L over 2 for both of the masses. So I1, I have an mr squared for this cylinder and mr squared for this cylinder over here. So I have m times L over 2 squared plus m times L over 2 squared. All right, so this comes out to ml squared over 4 plus ml squared over 4. Okay, and that equals ml squared over 2. So that's my initial moment of inertia. For my final moment of inertia, now it's slid a distance d apart from the, so now this cylinder got moved away some distance d, and then this cylinder got moved closer some distance d. Okay, so this distance here is still L, but my axis of rotation is here. So this distance is L minus d, and then this distance over here is going to be L plus d. Okay, so now I'm going to write it again. So I2 is equal to the moment of inertia of this cylinder on the left. So I have m times, wait a minute. L is the whole length. All right, you got to be careful. It's L over 2 plus d, L over 2 minus d. Got to be careful. So the L is the length of the whole rod. All right, so here I have m times L over 2 plus d quantity squared plus m times L over 2 minus d quantity squared. All right, so now we have to evaluate it. So here the L over 2 plus d quantity squared, I'm just going to write it all out. So I have m times L squared over 4. All right, and then we're going to be basically foiling this. So we have L over 2 times d plus L over 2 times d plus d squared. Okay, so that's the moment of inertia of the left cylinder. For the right cylinder, we have the same expression, except now it's minus d. So it's m times L squared over 4 plus, oh, whoops, almost made a mistake, minus, okay, because it's L over 2 minus d. Okay, so we have minus L over 2 times d minus L over 2 times d plus d squared. Now it's plus d squared because negative d times negative d is positive d squared. Okay, now if I add all these terms up, well, they're both multiplied by some factor m, so these terms cancel out. Okay, and then all I'm left with are the outer terms. All right, so if I put all that together, ml squared over 4 plus ml squared over 4, I have ml squared over 2, and then I have md squared plus md squared, so it's plus 2md squared. All right, so if I compare the moments of inertia, all right, I have ml squared over 2 for I1 ml squared over 2 plus 2 md squared. So obviously I2 has to be larger than I1. The moment of inertia for figure 2 is larger. And this relates to part B. So for part B, we need to figure out what the what omega 2 is. All right, so now we got to solve for omega 2. All right, so I have I2 omega 2 equals I1 omega 1. So that means that omega 2 is equal to I1 omega 1 divided by I2. All right, and that's going to be ml squared over 2 divided by ml squared over 2 plus d squared. And then all of that times omega 1. And that's going to be our expression. And then for part C, indicate whether the equation you derived in part B is consistent or not consistent with the claim in part A. Well, the claim in part A is that omega 2 is greater, right? So if I compare these two things, okay, I can clearly see, oh, whoa, wait. I said omega 2 is less. All right, it's less than omega 1. I misspoke because I was thinking of omega 1 being greater than omega 2. It's asking about omega 2. So the angular velocity in figure 2 is less than angular velocity in figure 1 because of the new mass distribution. In terms of the math, we have this expression, right? So I'll write it over here again. I have here omega 2 is equal to ml squared over 2 divided by ml squared over 2 plus d squared times omega 1. Well, clearly the denominator is bigger than the numerator, right? So this whole expression here has to be less than 1, right? Because I have ml squared over 2 divided by ml squared over 2 plus some positive constant. Okay, so the denominator is bigger. So that pretty much shows that it's consistent with our expression. And I guess in terms of cleaning up the expression, what can I do to write it in more elegant terms? I guess having complex fractions, it's not so nice. So we can multiply everything by, oh my goodness. Did I mess something up? Yeah, 2md squared. I knew I messed something up. And it is getting late. I'm tired. All right. Whoops. Right, because there's an md squared over here for the left cylinder, and there's an md squared over here for the right cylinder. So in total, it's 2md squared. My bad. 2md squared. And then I can basically factor out an m, right? So I can factor out an m. But actually, the m's just cancel out. There's an m in every single term, right? So the m's are just going to cancel out. I have m over m. So those m's cancel out. And then I have L squared. Or if I multiply everything by 2, okay, I have L squared over L squared plus 4D squared. That's the ratio times omega 1. All right, there we go. That's the answer to B, and then it's consistent with what we said in part C because the denominator is bigger than the numerator. So omega 2 has to be less than omega 1. And that's pretty much it. If you have any questions, definitely stop by after school so I can help out with the problems. And then this is also true for, obviously I don't have time to go over the multiple choice. And I set it up to where it tells you, you can check the answers and it gives the explanations for the multiple choice are pretty good. So if you have any questions on those, just let me know. And especially for these FRQs, right? If there's a part of the solution manual or a part of what I explained that you want me to elaborate more on, just stop by after school so that we can prepare for the test. All right. Well, anyways, good luck, study up, and then let me know if you have any questions. Oh.